Okay, so we're going to do the same limit again. But now we're going to use a graph. I will say a lot of the techniques we're learning today, you're not going to be using on your exams. Today is more just about kind of getting the intuition behind a limit and understanding the limitations of using a graph or a table of values, but also understanding they are powerful tools. I mean, for the most part, they do usually give you the right answer unless the function has kind of been cooked up to be tricky. All right, and you will see some examples like that in the homework. Okay, so now so what I mean by use a graph, I mean graph it and kind of from the actual graph, kind of just eyeball what is the limit. And so let's discuss how we actually do that. So for instance, how do you actually graph this function? So it's probably helpful to understand what this function really is. So remember the convention is if I give you an expression, I say, here's the function, the convention is the domain is the largest possible domain, but it's undefined otherwise. So for instance, this function is actually this fraction, but only if x is not equal to 3. Right? If x is actually equal to 3, this function is just undefined. Right? That's the convention. Okay. Now, my goal is to be able to graph this highlighted function. Let's do it without a calculator. Now, it looks like a very complicated expression, and in general, it would be, except we do get cancellation, which is nice. So let's go off to the side, and can we actually simplify this expression? Yes, right? We can factor the top and then cancel a common factor. So the top here factors as x minus 3, x plus 1. And then I can cancel out the x minus 3's, right? Why? Because I'm assuming x is not equal to 3 for that piece. I'm allowed to cancel it out. And I just get x plus 1. So in other words, this function looks very complicated. It actually isn't, right? This function really is in disguise. It's really just a line, right? It's x plus 1 if x is not equal to 3. And it's undefined if x is equal to 3. I kind of want to make a little subtle point here. This function f of x, this is not the function x plus 1. Because our function is undefined at x equals 3. But if I gave you the function, say, g of x equals x plus 1, g of x has domain all real numbers. Because I didn't tell you anything else, right? So you just assume it's as big as possible. But my function f is not defined at x equals 3. Do not let this kind of confuse you. Even though x plus 1 is perfectly acceptable for x equals 3, my original function is not defined at x equals 3. Okay? Let's see. So if someone has a question in chat, would there ever be a situation where you cancel factors x is equal to? I think what you mean by what if x is equal to 3? Can you cancel out the common factors? The answer is no, right? You can only cancel common factors if you are sure that in that context, that factor is not 0, okay? Because it's almost like saying, oh, 0 over 0, cancel out and I get 1. No, that's nonsense. 0 over 0 is undefined, right? So you cannot cancel out common factors unless you are sure that those factors are not 0. It's a good question. We're going to be kind of belaboring that point a lot. You're going to hear me say that a lot. Okay, so now this function's actually in a sufficiently simple form that we can actually just graph it. I mean, I hope everyone knows how to graph lines, right? Let's see if Dr. G knows how to graph a line. I always mess up because I never give myself enough room. So let's see. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this is the line x equals 1. Oh, sorry, y equals x plus 1. So that passes through the point y equals 1 on the y-axis, and then, let's see, 3, these 2 points. The nice thing about notability is that I can kind of just, okay, it's not really. Come on. There we go. Okay, so this is a graph of the function y equals f of x. Sort of. I have one little mistake here, right? Is this a graph of y equals f of x? I have to modify it very slightly. How do I modify this graph slightly?
You add a hole at x equals 3.
That's right. At x equals 3, I need to have a hole because this function is not defined at x equals 3. So first, let me kind of color that point. So this is the point we care about. This is the point 3, 4. But we know that our function is not defined at x equals 3, so I need to kind of erase that point. So I'm going to, so it should be an open hole like that. Okay, good. Now, how does the graph suggest that what the limit actually is?
When you look at it from the left and right, you can like see.
So okay, so Angelica started out and then she bailed. That's
Well,
okay, because Angelica knows the answer. She wants to make sure everyone else knows it.
when you look at the graph, you can see that as you're approaching 3, the y value is at 4. So it'll
Okay.
never like really get to 4. But
Okay, all right, good. Yeah, sometimes, you know, it's funny, sometimes things like this, you know exactly what you mean, and sometimes it's hard to explain it to other people, right? It's hard to explain it in your own words. So I think that explanation's pretty good. So let's see. So I like to kind of think about this visually. Where's x equals 3 on the x-axis? So right here, here's x equals 3. Now, did you know that in Notability, I can now do both dashed lines and dotted lines? Did you know that? It's pretty sweet. So in this case, so let's look at x equals 3. So what I do is I consider x values that are close to 3 on either side, right? So I'm like I'm going to trace out. I'm going to actually not use that dotted feature. So I trace out points that are close to x equals 3 on either side. And then I trace out the corresponding points on the graph. Okay, so corresponding points on the graph will then be, let's do this in green, all these marked points in green on the graph. And the question is, all those marked points on the graph, they all seem to be converging upon this open hole. Now, how does that help you calculate the limit? Remember, the limit is values of the function, right? This limit down here, circled in green, means you're asking, as x approaches 3, what happens to the values of f of x? And we know that graphically, the values of f of x correspond to the y coordinates of the graph, right? So all you have to say is, aha, the green values, y is approaching 4 for the green values. So therefore, that limit is approximately equal to 4. Now here's some bonus questions. So here's a bonus question. What if my function were just a little bit different? So
Why is 3 a closed hole?
3 is not a closed. Do you mean on the x-axis?
Yeah.
Remember, the x-axis is not part of the graph of the function. Okay. So the stuff I wrote in orange is nothing to do with the graph. It's just I was just kind of marking to you where x equals 3 was. It's not meant to be part of the graph. Okay, so let's look at this function here. Right now it's undefined at x equals 3. What if someone came along and said, you know what, I don't want it to be undefined. I'm going to make it equal to 2. How does the graph change? So if I wanted to graph this function now, what would I actually have to change? I would need to have, go ahead.
Oh, sorry. Wouldn't it be like a jump discontinuity? Like, would the graph be discontinuous?
Oh, so Emily has taken calculus before. She knows these words, jump discontinuity. So it's actually what's called, it's actually a removal discontinuity, not a jump.
Oh,
But you kind of have the right idea. There's kind of a little portion of the graph that's kind of off, right? Because this has to pass through the point x equals 3, y equals 2. So that means there would be a closed hole at, what, 3, 2, right there. And let's erase all this stuff so we can see kind of a clean version of this graph. Okay, so now what you see in purple is that is a clean version of this new version of the graph, right? If I said that f of x had to be equal to 2. Now let me ask you again, what is the limit? How has this changed?
It's the same.
It hasn't changed.
Hasn't changed? Okay, so Gabby, you were the first one to say it. Why would you say, Gabby, why has the limit actually not changed? So you're claiming, just to be clear, the limit is still 4. That's what you're saying.
Yeah.
Right. So why is the limit still 4? Do you want to explain it? Or do you want to pass it off?
Well, because it's asking for the limit of the function, but if it asked for the value of the function at x equals 3, then it would be 2. But
Okay,
it's
good.
just asking for the limit.
Okay, good. So that's perfectly correct, right? There is a difference between asking for the limit of the function and asking for the value of the function. This would be f of 3 equals 2. Right? Remember, when I'm asking for the limit of a function, in this case, x going to 3, do I care about what is happening at exactly x equals 3? No. The limit only cares about what happens as x approaches 3, but never quite is equal to 3. So it doesn't matter where this point is. This point can literally be anywhere you want, right? It can be filled in. It can be over here. It can just not even be on the graph, right? It can just be completely undefined like we had earlier. All that really matters is if I trace out values of x close to 3, and I trace out those points on the graph, all those points converge upon y equals 4. And that's all that matters for the limit. Now, Emily mentioned discontinuities. So we do care about the fact that, so in this particular example, if I do have something like this, where the limit and the function value are not the same, we do care about that, and we say that this function is discontinuous. So it's not that we don't care about this or that limits and function values are different. We actually have a whole class on just functions like this, where the function value is not equal to the limit. Okay. So let's, whoops, here we can keep that, but now we have to go back to, this was actually undefined. So let's just change everything back to the original example. So that was actually undefined. There is no point over here, and the limit is still 4. Okay, good. Any questions about that? Right. The big thing was, you know, the function value doesn't matter.